If you ask a standard path planning algorithm to navigate an obstacle course, it will draw a mathematically perfect line. But when you hand that exact same route to a physical robot, perfection and physical momentum break down. The problem lies in the sharp vertices of the generated path. Executing a true 90-degree turn without losing speed requires infinite angular acceleration. For non-holonomic systems, like a differential drive unicycle robot, instantaneous heading changes are physically impossible. The wheels can only move forward, backward, or rotate the chassis around a central axis. This plot shows a raw A-star output. The yellow path bypasses obstacles using discrete segments and sharp angles. These corners represent C0 continuity. The path is unbroken, but curvature is discontinuous. To follow this, the robot must completely stop, rotate, and reaccelerate. Repeating this start-stop sequence at every grid intersection creates severe impulse demands on the motors, draining actuator energy and significantly increasing travel time. Achieving the absolute shortest geometric route on a map does not yield a dynamically feasible route for a physical machine. This chart displays the mathematical solution to that acceleration problem, a cubic B-spline curve. By applying this algorithm, the jagged C0 vertices are replaced with continuous red arcs. The robot can now maintain a steady, unbroken velocity as it navigates the same obstacle course. Cubic B-splines possess three specific mathematical properties that perfectly bridge discrete spatial planning and continuous motion control. By deconstructing how the Cox-de Boer algorithm applies these properties, we can guarantee safe, non-stop navigation for any differential drive system. The process begins by parameterizing the trajectory using a degree 3 or cubic polynomial. The first defining property of this cubic polynomial is local support. As you move a single control point, only adjacent sections to form. The remaining trajectory stays unaffected. This keeps computational costs extremely low. If a waypoint shifts, the system recalculates only that specific segment. The second critical factor is the strong convex hull property. Connecting a subset of control points forms a translucent boundary, trapping the mathematical curve entirely inside. This establishes a hard safety rule. If your control points clear an obstacle, the trajectory will never intersect it. The third and most important property for physical mechanics is C2 continuity. It dictates that the path is unbroken, and its curvature, represented as kappa, is entirely continuous. There are no vertical spikes, providing the robot with smooth, progressive steering commands instead of impossible jumps. These three theoretical pillars, local adjustments, guaranteed obstacle clearance, and unbroken steering curves, create a highly robust framework for robotic motion control. With the theoretical properties established, the next step is assigning the physical control points to shape the curve. This graphic illustrates our raw material, sparse waypoints remaining after line-of-sight pruning. The system repurposes these orange pruned waypoints as gravitational anchors, pulling the cubic spline into shape. In panel B, we see the resulting blue Bezier trajectory rendered over the linear path. To ensure the robot actually begins and ends exactly where it needs to, the algorithm employs a uniform clamped knot vector. Clamping mathematically forces the generated curve to intersect the very first and very last waypoints with zero deviation. This parameterization laterally rounds off the sharp interior vertices for dynamic stability, while locking in the exact start and goal states required by the mission. We can now evaluate how this newly smoothed geometry dictates Newtonian physics constraints, specifically force, mass, and acceleration. This plot shows the unsmoothed line-of-sight path. The highest kinetic stress occurs directly at these sharp vertices. Without the spline applied, forcing a mass to decelerate to zero and immediately accelerate in a new direction maxes out the motor's impulse limits. Looking at the smoothed path in this chart, the dynamic forces change completely. Centripetal force is calculated as mass times velocity squared, multiplied by curvature. Because the B-spline turns the sharp corner into a sweeping arc, the robot can maintain a steady forward velocity. By calculating maximum safe curvature, the system explicitly caps the required centripetal force, preventing the tires from exceeding their physical traction limits. Geometric path smoothing is a direct method of bounding physical kinetic energy. To prove this pipeline works in practice, we test the mathematical output on a simulated differential drive Turtlebot. These charts detail raw curvature data from tracking the B-spline trajectory. The left graph measures curvature across arc length. The value remains tightly bounded and continuous. The right chart plots the curvature derivative. Crucially, there are no vertical infinite spikes anywhere on the timeline. This data confirms that the robot never faces a mathematical command that forces it to stop and rapidly reorient mid-drive. Passing these kinematic checks ensures that when the trajectory is handed off to the live model predictive control system, tracking remains predictable and error rates stay low. There is exactly one metric where the B-spline approach mathematically underperforms: total spatial path length. Because the spline rounds over the interior corners, the final route is marginally longer than the absolute shortest geometric path found by the initial search. But this spatial sacrifice yields massive physical dividends. Adding a few centimeters eliminates start-stop cycles, preserving momentum, slashing mechanical wear, and conserving battery energy. By integrating cubic B-splines into the navigation pipeline, the acceleration paradox is solved. It elevates a theoretically perfect map route into a highly efficient, production-ready framework for real-world autonomy.